One, two, one, two, one, two, one, two, one, two. Woo!
Hello guys and welcome back to this one. So as we said earlier, we're going to be doing one that falls into the criteria of the question, say no recursion, no stack, and space O of one. Say this guy would use a man called Morris Transversal, an ingenious way to use your tree as a stack, right, or memory. So basically we use our tree as a stack or memory to, like, help us remember stuff and help us go through the whole ordeal without having to use a storage or a stack. So we're going to do this our conventional way. We'll go through the code first off, and then we will then go through um the graphical illustration before the debugger tool. But as the last guy as well, the stack, this is also going to make sense more on in the with the graphical description, where we'll see how stuff goes through the tree basically, right? And yeah, so bear with me with the code if it gets a bit too technical. So yeah, let's get into it. We call again our inner transversal in order transversal optimization, and we take in a node. Now we switch from root to node. Variety is the spice of life. But yeah, current node. We point current to the node. See, because our base case we will have current end at none, right? So we say while current. So we are talking about the reason why we chose to say while current, because we're trying to get to the base of the node, right? So we say while current. So while current is not none, we say we can boldly move right because, right? Because we know the only situation where right will be none will be at the end, right? The tail of the tree. If not, if it's not the end, it will be pointing back to the previous current. So that would make sense again in the graphical illustration, but I'll try to also break that down here. It says if current or left is none, right? So current or left is none, print current dot value and then current dot right, then move to the right. We return the current to a once current or a previous current, depending on how you want to say that. Now we call a predecessor to the current dot left. So basically we go to the left and we instantiate a predecessor there. And okay, just to give like a bit of a context, even though we know we're not at the graphical description first. So basically what it's saying is that go to the left and call this guy a predecessor, and then when we do that, this is an if and an else case. So when we do the current dot left and the predecessor, so we say so transverse you meet the end of the right node. So it says while predecessor dot right and predecessor dot right is not current, that we should just go predecessor dot right. So we're just going to while loop till we meet a none here, right? So we're just going to increase our predecessor. Is our predecessor, so we have something like this over here. We have this guy come here, and when we call the while loop, is going to transverse down to this guy. So we say predecessor is equals to predecessor dot right. Predecessor dot right. So we say why predecessor dot right. So that means we are going to stop out the guy before the right becomes none. So basically the 3, right? So we go that we that's to know, and we say if predecessor dot right is none. I'm not sure I can keep calling this predecessor. Oh my gosh. It's a tongue biter. I think I'll just call it pred. Yeah, that will suffice. But yeah, so pre dot right equals to current, right? So we say current equals to current dot left. So what are we saying in that sense? That if the predecessor is right, right? Oh, sorry, the right is none. So like in this situation here, where we'd have its right as a none, right? That's that. What do we want? We want the predecessor, the right to then point to current. So initially depends on where we find the current. The current in this situation should ideally be this guy. So we should now point this guy up to it. But yeah, this, as I said, would make sense in the graphical video that is coming up next. So current equals to current dot left. And yeah, we then move to the left again in a sense to, because now this our right is now pointing to this guy, and then we move our current to the left. Else, if the situation where we have the predecessor right is not known, basically that's the else, then we could say predecessor right should become none, and then we print out the current value, and current is equal to current dot right. So this video is basically just to show some kind of helper, to give us clarity of what most of these guys are, basically how they will look when we get into the graphical illustration, because that's where we get to break stuff down more readily and more descriptively, so everything begins to open up. So as I said again, bear with me on this video, as on next video everything will be expanded on. And then we see print. This is the Morris transversal, and the Inorder Traversal basically is called here. So yeah, so that's it for this video. Can't wait to get into the graphical video where we begin to see stuff, right? And yeah, that's it for this one. Muchas gracias. Auf Wiedersehen. Tschüss.